Okay, so now that we have discussed functions, we can discuss limits of functions. So we begin our discussion of limits. This will take a few lectures. Okay, we're going to do the definition, what we mean by a limit, or at least informally what we mean by a limit, and then we're going to take a few examples of limits. Okay, so this notation here means, and this is the way you read it, the limit as x goes to x naught of f of x is equal to L. So L is some function. It takes an input x and produces some output, which is not necessarily L. Okay. So what this means is that as x gets arbitrarily close to x naught without ever touching x naught, then the value f of x gets arbitrarily close to L. Okay, so we do a few examples. And you'll see maybe more clearly what that means. Okay, so let's think about this graphically. Supposing that that green curve is the graph of some function, and then our x naught is 0 in this case. So as x gets really, really close to 0, the function values on this graph are getting really, really close to 0. If you look at the red curve, that maybe is the graph of another function. And again, when x is getting really, really close to 0, the function value along the y-axis, those are getting very, very close to 0. And if you look at the blue curve, that's a somewhat more complicated function. And its values, as you take x values very, very close to 0, the points x, y on the curve, the y values are also getting very, very close to 0. So for all three of these functions, we should say that the limit as x goes to 0 of f of x is equal to 0. The limits are a bit more complicated than this, but let's take the example of a continuous function. Okay. So f is the function which sends r to r. It has codomain, it has domain r and codomain r, and it's defined by f of x is equal to pi. So whatever value x you give it, f spits back the value pi. Okay. So the range of this function is just pi. It's the set which just contains a single element pi. Now I want you to evaluate the limit as x goes to 7 of f of x. Well, okay. As x gets really, really close to 7, so let's imagine that we're taking values like, I don't know, 6.9. F of 6.9 is pi. F of 6.99 is pi. F of 6.999 is pi, and so on and so forth. As you get really, really close to 7, without ever touching 7, so f of 7.1 is pi, f of 7.01 is pi, f of 7.001 is pi, and so on. Then the function values are arbitrarily close to pi. Okay? And this would be the algebra that you would do to evaluate the limit. The limit as x goes to 7 of f of x equals the limit as x goes to 7. Okay, as x is getting really, really close to 7, f of x is taking the value pi. So it's the limit as x goes to 7 of pi, which is pi. Okay. Now let's take another example. F sends r to r, defined by f of x equals x. So the domain is the reals, the codomain is the reals, and the range, well, all the values that f takes, well, those are all of the reals. So the range of f is also all of the reals. Now we are asked to evaluate the limit as x goes to 7 of f of x. Well, just intuitively, As x gets arbitrarily close to 7, x, the function value, which is x, is getting arbitrarily close to 7. So I would say that the limit is 7. Okay, so let's see what happens. Okay, we would write it, we would say the limit as x goes to 7 of f of x equals the limit as x goes to 7. Now what form does f of x take? It's x. And so then this says, as x gets arbitrarily close to 7, what value does x get arbitrarily close to, which is 7. All right. Let's take an example from a graph. So we see here that x, let's say, is getting really, really close to some value on the x-axis, x naught. And the y value at x naught, right? See, the function values are or the points of the graph are in blue, right? So there's a blue dot on the x-axis, which is where y is equal to 0. So f of x naught is equal to 0, right? But now let's think about it. As we take values that are really, really close to x naught, then the y values are the height of this red circle. So whatever that height is, that's the limit, right? Not the function value x naught. So the limit value can be different than the function value. Okay, so let's see an example of that. We're going to define f since r to r by f of x is equal to, it's defined in two pieces. When x is not equal to 7, f of x is equal to x. And when x is equal to 7, f of x is equal to 5. Okay, the domain of this function is the reals, the codomain is the reals, and the range is, think about the range for a minute. Yeah, what would the range be? Well, if we exclude x is equal to 7, you get all the numbers except when x is equal to 7, and then when x is equal to 7, f of x is again equal to f of 5, which is 5. So the range seems to be all of the reals except for 7, right? There's no input x such that f of x is equal to 7. Okay, so I'll ask you to think about this. Let's evaluate the limit as x goes to 7 of f of x. Okay, so the limit as x goes to 7 of f of x is equal to the limit as x goes to 7. Now, when x is really, really close to 7 but is not equal to 7, what is the form of f of x? Then f of x equals x, the way we defined it. So the limit as x goes to 7 of f of x equals the limit as x goes to 7 of x. Now, what does that say? That says, as x gets arbitrarily close to 7, what does x get arbitrarily close to? Oh, 7. Okay. So the function value is 5, but the limit value is 7. Okay, so the function value and the limit value are not always the same thing. Okay. Let's take this one. F is the domain of this function is the reals except for 1. And let's say the codomain of this function is R. And f of x is equal to, defined by f of x is equal to x minus 1 divided by x minus 1. So the function isn't defined when x is equal to 1. And otherwise, the function values would all seem to be 1. So the range of this f is the set consisting only of 1. Okay, let's evaluate this function. And let's evaluate the limit. as x goes to 1 of f of x. Okay. Well, the limit as x goes to 1 of f of x is equal to the limit as x goes to 1 of x minus 1 divided by x minus 1. That's how we define the function. Now, when x is not equal to 1, you're allowed to cancel. I mean, you never want to be dividing by zeros, but this says that x is getting really close to 1, but is never equal to 1, in which case x minus 1 is not 0. So x minus 1 can cancel with x minus 1, and that'll give us 1. Okay, so the limit as x goes to 1 of f of x is equal to the limit as x goes to 1 of 1. And as x gets arbitrarily close to 1, 1 is arbitrarily close to 1. Okay, so that's the limit. The limit is 1. And notice that the function isn't even defined at x is equal to 1. Okay, okay, let's take a look at a graph here. So here the graph seems to come in pieces. There's one piece, and then there's a piece which is a single point, and then there's a third piece which is another smooth curve. Okay, so if we take values that are arbitrarily close to x naught, x values that are arbitrarily close to x naught, but are never actually equal to x naught, then and remember, you approach x naught from both sides. Numbers that are bigger than x naught and numbers that are less than x naught. So when you're taking numbers which are bigger than x naught and you ask what is f of x, then you're getting numbers that are close to the y value of the higher red circle. And if you're going from the left and you're taking values that are really, really close to x naught, then you are getting y values that are very close to the height of the lower red circle. So there is no single value that your function values are getting closer and closer to. So in this case, the function value is 0. The function exists at x, the function is defined at x naught. The value of the function at x naught is 0, and there is no limit value. Okay, the limit, it does not exist. Okay, let's see an example of something like that. Okay, so we define f maps reals to reals by f of x is equal to 1 for positive numbers x, and it's equal to 0 otherwise. Okay, so the domain is the reals, the codomain is the reals. The range of the function is the set consisting of the two elements, 0 and 1. Now, let's take the limit as x goes to 1 of f of x. The limit as x goes to minus 1 of f of x. And the limit as x goes to 0 of f of x. Okay. Well, the limit as x goes to 1 of f of x. Well, as if x is getting really, really close to 1, then we have positive numbers. And when the input x is positive, then f of x gives you a value 1. So the limit as x goes to 1 of f of x equals the limit as x goes to 1 of 1. And as x gets really, really close to 1, the value 1 is arbitrarily close to 1. Let's look at the second limit. If you're taking the limit as x goes to minus 1 of f of x, well, if x is really close to minus 1, then x is negative. When x is negative, f of x is 0, the way we've defined this function. So the limit as x goes to 1, minus 1 of f of x, equals the limit as x goes to minus 1 of 0. So as x is getting really, really close to minus 1, 0 just sits there being 0, and it's arbitrarily close to 0. Okay. Now consider the third one. You're taking the limit as x goes to 0. Well, let's consider that you're taking you're on an interval about 0. 0 is at the center of this interval. From minus delta to plus delta, you pluck 0 out of that. Now you take the function value of some number which is negative. You get f of that x is 0. Then you take the function value of some point where the number is positive, very close to 0, but still positive, and you'll get the value 1. No matter how small you shrink this interval, whenever you pick a point out of that interval, you will get 0, and you can take another point out of that interval and you can get 1. So as you keep shrinking the interval, and you're taking points which are closer and closer to x is equal to 0, you're still getting function values 0 and 1 on the interval. So it isn't settling down to a single value. The function values are not getting arbitrarily close to one particular value. These two values, 0 and 1, keep coming up. So in that case, we say that the limit doesn't exist. When we'll discuss this again when we consider the directional limits. Okay, so we've discussed the we have discussed the definition of limit, and we've discussed we've taken a few examples of limits, and next we will consider a few ways of how you go about calculating limits. Okay.